Have you ever realized that right now, something completely invisible is pulling on every single object around you? Your body, your bed, the walls, even the air in the room. And yet you can't see it, touch it, or turn it off. This invisible force is so powerful that it holds oceans on Earth, keeps the moon from drifting away, and controls the motion of entire galaxies across the universe. But here's the strange part. Despite ruling the cosmos, gravity is still one of the biggest mysteries in science. Tonight, we're going to slowly explore the most fascinating and relaxing facts about gravity, starting with the quiet force holding you to Earth right now. Right now, as you are sitting or lying down, something very powerful is quietly acting on your body. You cannot see it, you cannot hear it, and you cannot feel it directly, but it is always there. That invisible force is gravity. At this very moment, gravity is gently pulling your body toward the center of Earth. The reason you don't notice it is because this pull has been constant your entire life. Your muscles, your bones, and even your sense of balance have grown used to it. In fact, if gravity suddenly became stronger or weaker, you would notice the change immediately. Walking would feel strange, standing would feel different, and even lifting your arm could feel unusual. The interesting thing is that gravity is not only pulling on you, it is also pulling on every single thing around you at the same time. The chair, the floor, the walls, and everything inside the building are all being pulled toward Earth in the same quiet and steady way. Now think about the room around you. Look at the table, the chair, the phone, or any object nearby. Every one of those things is being pulled downward at this exact moment. Gravity is acting on them all together, all the time. The reason nothing seems to be moving is because those objects are supported by something underneath them. The table is supported by the floor. The phone is supported by the table. The building itself is supported by the ground. Gravity keeps pressing everything toward Earth, while solid surfaces stop objects from going any farther. This balance is what keeps the world around you stable and calm. If gravity did not exist, things would not stay where you left them. Your cup would not stay on the table, and your phone would not stay in your hand. Everything would slowly move away from the surfaces that normally hold them. It might seem strange to imagine, but the stillness of your room is actually the result of gravity constantly doing its quiet work. Now think about the bed you are resting on right now. The reason your body stays comfortably on the mattress is because gravity is pulling you downward, while the mattress pushes upward to support your weight. This simple balance is something we experience every day without thinking about it. Gravity pulls your body toward Earth, and the bed provides resistance so you remain supported. That is why you stay in place instead of floating in the air. Imagine how different sleeping would feel if gravity did not exist. Your body would not stay on the bed at all. Even a small movement could send you slowly moving away from the mattress. Astronauts experience something similar in space stations. Because they are constantly moving around Earth in orbit, they feel almost weightless, and they must strap themselves into sleeping bags so they do not move around while they sleep. Here on Earth, gravity quietly keeps you comfortable and stable, allowing you to rest without even thinking about it. Now here is an interesting thought experiment. Imagine that gravity suddenly stopped working for just 5 seconds. It sounds like a short time, but the results would be surprising. The first thing you would notice is that nothing would stay where it normally rests. Objects that depend on gravity to stay in place would begin moving away from the surfaces that support them. The cup on your table would leave the table. Papers, dust, and small items would begin moving through the room. Even the air around you would no longer stay close to the ground the way it normally does. For a brief moment, the room would become a place where everything is free from the pull that normally keeps it stable. But here is the important part. The moment gravity returned, everything would fall back toward Earth again. Objects would come down quickly, landing on the floor or other surfaces. This simple idea shows just how important gravity is for keeping our everyday world stable and predictable. If you look closely at a beam of sunlight coming through a window, you may notice tiny dust particles slowly moving in the air. These particles are extremely small, far lighter than anything you normally hold in your hand. Yet even these tiny pieces of dust are being pulled by gravity. The same invisible force that pulls your body toward Earth is also pulling on every dust particle in the room. The reason dust does not immediately fall to the floor is because the air around it keeps pushing it in different directions. Small air movements, caused by breathing, walking, or even warm air rising, can keep dust floating for a while. But gravity never stops pulling. Slowly and patiently, it continues pulling those particles downward. Eventually, many of them settle on surfaces like tables, shelves, and floors. That thin layer of dust you sometimes see on furniture is actually proof that gravity has been working quietly over time, guiding even the smallest particles back toward the ground. Now here is something that surprises many people. Even though gravity controls huge parts of the universe, scientists say it is actually the weakest force in nature. This may sound strange at first. After all, gravity keeps you on the ground, holds oceans on Earth, and keeps the moon moving around our planet. So how could it be weak? The answer becomes clearer when we compare gravity with other forces in physics. For example, the forces that hold atoms together inside matter are incredibly stronger than gravity. Even a small magnet can lift a paperclip against the pull of Earth's gravity. That simple example shows how powerful other forces can be. Gravity, in comparison, is much weaker when acting between small objects. However, gravity has one special advantage. It works between all objects that have mass, and it works across very large distances. Because of this, when huge objects like planets and stars are involved, gravity becomes the main force shaping their motion. Even though gravity is considered weak compared with other forces, it still controls some of the largest structures in the universe. The reason is simple but fascinating. While other forces act strongly only at very tiny distances, gravity works across enormous distances. It connects objects that are millions or even billions of kilometers apart. Because of this, gravity becomes the force that guides the motion of planets around stars. In our own solar system, every planet follows a path around the sun because of gravity. The sun's huge mass creates a powerful pull that keeps those planets moving in stable paths. But the story does not stop there. Gravity also keeps stars gathered together inside galaxies. Our galaxy, the Milky Way, contains hundreds of billions of stars, all connected by gravity. Even groups of galaxies move around each other because of this same force. So while gravity may seem weak in small situations, when enormous masses are involved, it becomes the quiet organizer of the universe. One of the most remarkable things about gravity is that it never stops working. It does not need energy, it does not rest, and it does not switch on or off. Gravity is always active, every second, everywhere in the universe. Right now, while you are sitting or relaxing, gravity is continuing its work all around you. It is holding your body to the ground, keeping the atmosphere close to Earth, and guiding the moon in its path around our planet. At the same time, far away in space, gravity is guiding planets around distant stars and keeping galaxies together across vast distances. Another interesting detail is that gravity works completely silently. Unlike wind, waves, or moving machines, gravity makes no sound at all. It simply acts in the background, steady and reliable. Because it never pauses, Gravity has been shaping the universe for billions of years, slowly organizing matter into the stars, planets, and galaxies we see today. When we think about things moving through space, we usually imagine light, sound, or wind. But these things can be stopped or blocked. Light can be blocked by a wall. Sound can be reduced by thick doors or heavy materials. Gravity works very differently. It does not get stopped by walls, mountains, or even entire planets. Gravity moves through everything without being blocked. Right now, Earth's gravity is passing through the floor, through the bed, and through every layer of the building around you. It does not slow down or disappear when it meets an obstacle. Scientists find this very interesting because most forces interact with matter in complicated ways, but gravity simply continues through it. This is one reason gravity can influence objects over extremely large distances. The gravity of the sun reaches every planet in the solar system. Even objects very far away still feel that pull. So while walls can stop light and materials can stop sound, gravity quietly continues its path through everything. Now think about what happens when you go to sleep at night. Your body becomes still, your eyes close, and the world around you feels calm and quiet. But while you are resting, gravity is still busy working everywhere in the universe. On Earth, gravity continues holding the oceans in place and keeping the atmosphere close to the planet. The moon keeps moving around Earth because gravity guides its path. Far beyond our planet, the same force is controlling the movement of planets around distant stars. Even entire galaxies are slowly moving because gravity is pulling them toward one another. None of this stops when people sleep. The universe continues its motion in a steady and predictable way. Stars continue their journeys, planets follow their paths, and cosmic structures slowly change over time. All of this happens quietly, without anyone noticing in daily life. So while you relax and sleep peacefully, gravity continues shaping the universe, moment by moment. Here is something that may sound surprising at first. Gravity does not only exist between large objects like planets or stars. It actually exists between every object that has mass. Mass simply means that something contains matter. This includes large objects like mountains, but also very small things like a pebble or even a grain of sand. Because of this rule, every object in the universe is pulling on every other object with gravity. The reason we do not notice this in everyday life is because the pull between small objects is extremely tiny. For example, two small stones placed near each other are technically pulling toward one another. However, the force is so weak that it is impossible to see the movement. When objects become very massive, like planets or stars, the pull becomes strong enough to control motion. This simple idea is one of the most important rules of physics. Gravity connects everything with mass, creating a web of attraction across the entire universe. Once you understand that gravity exists between every object with mass, something interesting becomes clear. The Earth is pulling on you, but at the same time, you are also pulling on Earth. This might seem strange because we usually think of gravity as something that only large objects create. But according to the laws of physics, gravity works both ways. When two objects interact through gravity, each object pulls on the other. The reason you do not see Earth moving toward you is because the difference in mass is enormous. Earth is incredibly massive compared with a human body. Because of this, the effect of your gravity on Earth is extremely small. Technically, it still exists, but it is far too tiny to notice. However, the idea itself is fascinating. Every person, every animal, and every object on Earth is slightly pulling on the planet itself. This shows that gravity is not just something we experience from Earth. It is a shared interaction between all objects that have mass. When you learn that every object pulls on every other object with gravity, a natural question appears. If you are pulling on Earth, then why doesn't Earth move toward you? The answer becomes clear when we think about mass. Mass is the amount of matter inside an object. Earth has an enormous amount of mass. It contains mountains, oceans, forests, cities, and everything living on the planet. Compared with that, the mass of a single human body is extremely small. Because Earth is so massive, the effect of your gravity on it is almost impossible to notice. The pull exists, but it is incredibly tiny. Instead, Earth's gravity easily pulls you toward the ground. You can imagine it like a small pebble next to a huge mountain. The pebble cannot move the mountain, but the mountain's weight easily keeps the pebble in place. This simple difference in mass explains why Earth stays steady while we feel the pull of gravity. Now here is an important rule that helps explain how gravity works across the universe. The strength of gravity depends strongly on mass. In simple words, the more massive an object is, the stronger its gravitational pull becomes. A small rock has very little gravity because its mass is small. But a large planet has far more mass, so its gravitational pull is much stronger. This is why planets can hold moons in orbit around them. The same idea applies on a much larger scale with stars. The Sun has an enormous amount of mass compared with the planets around it. Because of this, its gravity is strong enough to keep all the planets moving in paths around it. If the Sun were smaller and had less mass, its gravitational pull would be weaker, and the planets might not stay in stable orbits. This rule is simple but powerful. Mass acts like the strength behind gravity, deciding how strongly an object can pull on everything around it. Mass is not the only thing that controls gravity. Distance also plays a very important role. The farther two objects are from each other, the weaker the gravitational pull between them becomes. You can imagine gravity like a connection between objects that becomes thinner as the distance grows. When two objects are very close, the pull between them is stronger. As they move farther apart, that pull becomes weaker and weaker. This is why the moon feels Earth's gravity strongly enough to stay in orbit. But a distant object far beyond our solar system does not feel Earth's pull in any noticeable way. The same rule works with the Sun. Planets that are closer to the Sun experience stronger gravity from it than planets that are very far away. Distance spreads the influence of gravity over larger space, reducing its strength. Understanding this idea helps scientists explain the motion of planets, moons, and many other objects in space. Scientists have even discovered a very precise rule about how distance affects gravity. The rule says that if the distance between two objects becomes twice as large, the gravitational force does not simply become half as strong. Instead, it becomes 4 times weaker. This may sound surprising at first, but it is a key principle in physics. Imagine two objects close together, pulling on each other with gravity. Now imagine moving them twice as far apart. You might expect the force to reduce by half, but in reality it reduces much more. It becomes 4 times weaker. If the distance becomes 3 times larger, the force becomes 9 times weaker. This pattern shows how quickly gravity weakens as objects move apart. Because of this rule, very distant objects in space have very little gravitational influence on each other. This mathematical relationship helps scientists predict the motion of planets, moons, and satellites with great accuracy, allowing us to understand how objects move through space. When scientists combined the ideas of mass and distance, they realized something surprising. The same simple rule of gravity explains many different events around us. It explains why an apple falls from a tree and lands on the ground. It also explains why the moon stays near Earth instead of flying away into space. At first, these two situations may seem completely different. One happens in a garden with fruit falling from a branch, while the other involves a giant object moving around a planet in space. But gravity connects them through the same rule. Objects with mass pull on each other, and the strength of that pull depends on how massive they are and how far apart they are. This single rule helps scientists understand falling objects, moving planets, and even the paths of comets. It shows that the universe follows consistent patterns. From small events on Earth to large motions in space, gravity quietly guides how objects move. For most of human history, people did not know why objects always fall toward the ground. They could see the result clearly. When a rock slipped from someone's hand, it always moved downward. When fruit separated from a tree branch, it always came toward the ground. This happened so consistently that people simply accepted it as a natural part of life. However, the deeper question remained unanswered. Why downward? Why not sideways or upward? Ancient thinkers had many ideas. Some believed objects moved toward the ground because that was their natural place. Others believed the earth somehow attracted things, but they did not fully understand how or why. For thousands of years, this mystery continued. People observed falling objects every day, but the true explanation was still unknown. The answer required careful thinking and observation. Eventually, during the scientific revolution in Europe, new ideas began to appear that slowly revealed the real reason behind this everyday event. One of the most important moments in understanding gravity happened during the 1600s, when a scientist named Isaac Newton began studying motion and forces. Newton lived in England and spent many years thinking about how objects move. During this time, scientists were already learning new things about planets and stars. Astronomers had observed that planets followed regular paths around the sun. However, no one fully understood what force kept them moving in those paths. Newton began asking deeper questions about motion on Earth and motion in space. Could the same rules apply to both? Instead of studying only the sky or only objects on Earth, he tried to connect the two. He carefully examined how forces cause objects to move and how those forces might work over long distances. Slowly, through observation and mathematical thinking, Newton started developing ideas that would eventually explain gravity in a clear and powerful way. One story often told about Newton describes him observing an apple falling from a tree. Whether the event happened exactly that way or not, the idea behind it was important. Newton wondered why the apple moved toward the ground. Then he asked a bigger question that few people had considered before. If Earth pulls the apple downward, could it also be pulling on the moon? The moon does not fall straight down like an apple, but it moves around Earth in a steady path. Newton realized that both events could be explained by the same force. The Earth's gravity pulls the apple toward the ground. At the same time, it pulls on the moon as well. The difference is that the moon is also moving sideways through space, so instead of falling straight down, it continues moving around Earth in orbit. This idea connected everyday events on Earth with the motion of objects in space, revealing gravity as a universal force. The gravity you feel every day, when you stand, walk, or sit, comes from the enormous mass of Earth. Our planet is incredibly large, made of rock, metal, water, and many deep layers beneath the surface. All of this matter creates a powerful gravitational pull. Because Earth has so much mass, its gravity is strong enough to hold oceans, mountains, cities, and the atmosphere close to the planet. When you feel your feet pressing against the ground, that is gravity pulling your body toward Earth. The ground simply pushes back, stopping you from moving any farther. This is why your weight exists. If Earth were smaller and had less mass, its gravity would be weaker, and everything on the planet would feel lighter. You would jump higher, objects would fall more slowly, and the atmosphere might not stay close to the surface. So the strong gravity we experience every day is directly connected to the huge amount of mass that makes up our planet. At first, it might seem like gravity pulls objects straight toward the ground beneath your feet. But the real direction of gravity is slightly different. Earth does not pull objects toward the ground surface itself. Instead, it pulls everything toward its center. Imagine the planet as a giant sphere. The gravitational pull from all of its mass points toward the middle of that sphere. No matter where you stand on Earth, gravity is guiding you toward that central point deep inside the planet. The ground simply blocks your path before you can move any farther. This idea explains something interesting. When you drop an object, it moves downward because that direction leads toward Earth's center. But if you were standing somewhere else on the planet, down would point in a different direction, still leading toward that same central location. So the direction we call downward is actually just the path that leads from your position toward the center of Earth. Once you understand that gravity pulls everything toward Earth's center, another fascinating idea appears. People living in different parts of the world are all being pulled toward that same central point. Imagine someone standing in South America, someone in Africa, and someone in Asia. Even though they stand on different sides of the planet, gravity pulls each of them toward the middle of Earth. From their perspective, the ground beneath their feet feels like the bottom. Yet from another person's perspective across the planet, they might appear upside down. In reality, no one feels upside down because gravity always pulls them toward the center. This shared direction keeps everyone firmly attached to the surface of the planet. It may seem strange at first to imagine people standing on what looks like the side or bottom of a sphere, but gravity makes it completely natural. The pull toward Earth's center keeps every person securely connected to the planet. Even though gravity feels the same in most places on Earth, it is not exactly identical everywhere. One interesting example happens at very high altitudes, such as the tops of tall mountains. When you stand on a mountain, you are slightly farther from the center of Earth compared with someone standing at sea level. Remember the rule about distance affecting gravity. When the distance increases, even by a small amount, the gravitational pull becomes slightly weaker. Because mountain peaks are higher above Earth's center, gravity there is a little weaker than it is lower down. The difference is small, so most people cannot notice it in daily life. However, very precise scientific instruments can measure the change. This means that if you weighed yourself at sea level and then weighed yourself again on a very tall mountain, the number would be just a tiny bit smaller. This small change shows how gravity slowly weakens as distance from Earth's center increases. Even though astronauts appear to float effortlessly while inside the International Space Station, they are still feeling the pull of Earth's gravity. Many people assume that there is no gravity at that height, but that is not true. The space station orbits Earth about 400 kilometers above the surface. At this distance, the planet's gravitational pull is only slightly weaker than it is on the ground. Gravity at this altitude is still strong enough to affect the station and everything inside it. The reason astronauts seem weightless is not because gravity has disappeared. It is because both the station and the astronauts are falling together at the same speed. Gravity continues to pull on them constantly, keeping them moving along their path around Earth. So while it looks like they are floating freely in space, they are actually under the steady influence of Earth's gravity, moving in perfect coordination with the station itself. At the altitude of the International Space Station, gravity is about 90% as strong as it is on the surface of Earth. This is surprisingly strong, considering how far away they are from the planet. It shows just how massive Earth is and how its gravity extends far beyond the surface. Astronauts inside the station do not feel this full force in the usual way because they are moving rapidly around the planet. Their speed combines with gravity in such a way that they continuously fall toward Earth but never actually reach it. Instruments on the station can measure the pull of gravity directly. Even objects floating inside the station are under its influence, but they do not seem to move because everything is accelerating together. This measurement helps scientists understand not only how to maintain orbit, but also how gravity behaves at different distances from Earth, showing how the force extends far into space. The reason astronauts appear to float is fascinating when you understand the concept of continuous motion. The International Space Station and everyone inside it are constantly falling toward Earth. But because the station is moving forward at a very high speed, it keeps missing the planet. This combination of falling and forward motion means they stay in a circular path around Earth instead of hitting the surface. In other words, the astronauts are falling, but their forward motion keeps them in orbit. This motion is smooth and continuous, so they do not feel the pull in the same way we do on the ground. Objects inside the station float because they are all falling together at the same rate. This creates the illusion of weightlessness. Even though gravity is still acting strongly, the motion of falling around Earth makes the experience feel very different from standing on the surface. This continuous falling motion around Earth is what scientists call orbit. Orbit happens whenever an object moves forward fast enough while being pulled by gravity. Gravity is the force that keeps the object moving in a curved path instead of moving straight into space. For the International Space Station, this path is very close to circular, allowing it to complete one orbit roughly every 90 minutes. Other objects, like satellites and the Moon, follow similar principles, but each orbit depends on the speed of the object and the strength of gravity acting on it. Orbit is not just a concept for astronauts. It is the reason planets stay around the Sun, why moons stay around planets, and how artificial satellites can provide communication and weather information. The idea of orbit shows how motion and gravity work together in a perfect balance. Even in space, far from the surface, gravity controls movement, creating predictable and steady paths for objects in motion. Orbit is a remarkable example of balance in nature. It happens when two forces, gravity and motion, work together perfectly. Imagine an object moving forward very fast, like a satellite or a space station. Gravity is constantly pulling it toward the planet below. Without gravity, the object would continue in a straight line, moving away from Earth into space. But because gravity is pulling it inward at the same time, the forward motion bends into a circular or elliptical path. This is what we call orbit. The object is technically falling toward the planet, but because it is moving forward fast enough, it never reaches the surface. Everything in orbit follows this balance. From the Moon around Earth, to Earth around the Sun, and even the planets around distant stars, orbit demonstrates the quiet power of gravity combined with motion. It is a continuous and gentle dance, happening in perfect harmony across the universe, controlled by the rules of physics that govern every moving object. Without gravity, the Moon would not stay near Earth. The Moon has mass, and like everything else in the universe, it naturally moves in straight lines unless acted on by a force. Gravity from Earth is that force. If Earth's gravity did not exist, the Moon would simply continue moving in space in a straight line, no longer following a path around our planet. Over time, it would move farther and farther away. The Moon's presence in the night sky, its familiar shape, and the cycles of tides we experience on Earth all depend on gravity keeping it in place. This invisible pull ensures that the moon does not escape into the darkness of space. Even though the moon is far from Earth, gravity reaches across the distance to hold it gently in orbit. Without that constant pull, the moon would no longer circle Earth, and the natural rhythms we are familiar with would be completely different. The reason the moon remains near Earth is that gravity effectively traps it in orbit. The moon is constantly moving forward, but Earth's gravitational pull bends its path into a stable circle around the planet. This balance has lasted for billions of years, allowing the moon to follow a predictable path without colliding with Earth or flying away. Gravity ensures that the moon remains close enough to affect tides and illumination on Earth, but far enough to avoid a collision. The relationship between Earth and the moon shows how gravity controls motion over long distances. This same principle applies across the solar system, where planets, moons, and other objects are held in orbits by gravity. The moon's orbit is a clear example of how a massive object can guide the motion of a smaller one, creating stability over time. Without this balance, life on Earth would experience dramatic changes, highlighting the quiet importance of gravity in maintaining the natural order around our planet. At the same time, the moon itself has gravity, and it pulls gently on Earth. Although the moon is much smaller than our planet, its gravitational pull is strong enough to affect the oceans. This is why we have tides. As the moon moves along its path, its gravity pulls on the water, creating a rise in sea levels on the side facing the moon. There is also a smaller effect on the opposite side of the planet. The combined forces create a regular cycle of high and low tides, influencing life along coastlines. The moon's gravity also slightly affects the Earth's crust, causing subtle changes in the ground over long periods. This gentle pull is constant and predictable, showing how even a smaller object can influence a much larger one when gravity is involved. The moon and Earth are engaged in a quiet gravitational interaction, shaping the oceans, the land, and the natural rhythms we experience every day. The gravitational pull of the moon on Earth is surprisingly strong, even though the moon is much smaller than our planet. Its gravity affects the oceans directly, pulling water toward the side of Earth facing the moon. This pull is powerful enough to move enormous amounts of water across thousands of kilometers. Entire oceans rise and fall in response to this gentle tug, creating high tides in some places and low tides in others. The effect is not just on small areas, it happens globally, influencing coastlines around the world. Ships, marine life, and coastal ecosystems all experience the impact of this continuous movement. The oceans respond slowly, giving a calming rhythm that repeats twice each day. Even though we cannot see the pull of the moon, its influence on Earth's water is obvious. This demonstrates how gravity, though invisible, can create massive effects, moving large bodies of water and controlling patterns on our planet in a quiet but powerful way. The rising and falling of tides on Earth are directly caused by the moon's gravitational influence. As the moon moves along its orbit, it pulls on the water closest to it, creating a high tide. At the same time, the water on the opposite side of Earth also rises slightly, creating another high tide due to the balance of forces. Areas in between experience low tides as the water moves toward the regions of high tide. This cycle repeats predictably as the moon travels around the planet, creating a natural rhythm that has existed for billions of years. Tides affect many aspects of life, from fishing and navigation to the movement of ocean currents. Scientists can even use tides to study the moon's orbit and Earth's rotation. This phenomenon is a clear example of how gravity, although invisible and constant, controls the motion of water across the globe, shaping the planet's environment in ways we experience every single day. Interestingly, the moon is slowly moving away from Earth over time. This may seem surprising because we often think of the moon as fixed in the sky. In reality, the moon is gradually increasing its distance from our planet. This happens because of the transfer of energy between Earth and the moon caused by gravitational forces. The pull of the moon on Earth creates tides, and the friction of these tides slowly transfers rotational energy from Earth to the moon. This causes the moon to move outward, while Earth's rotation gradually slows down very slightly over long periods. The process is extremely slow, so humans do not notice it directly in daily life, but it is measurable by scientists using precise instruments. This gradual change reminds us that even something that seems stable, like the moon in the sky, is actually slowly moving and changing because of gravity's persistent influence over billions of years. Every year, the moon moves about 3.8 centimeters farther away from Earth. This tiny change seems almost impossible to notice, yet scientists have measured it carefully using laser reflections from mirrors placed on the moon during Apollo missions. The small increase may not affect our daily life, but over millions or billions of years, it can change the length of days on Earth and the pattern of tides. The movement is caused by the ongoing interaction between Earth's rotation and the moon's gravity, which transfers energy slowly. This shows that gravity is not just a force keeping the moon near Earth, but also a dynamic influence that changes over time. Even such small yearly movements are evidence of the constant, invisible work of gravity shaping our planet and the moon's orbit. This gentle expansion is a reminder that everything in the universe, no matter how stable it seems, is subtly affected by gravity every moment. Billions of years ago, the moon appeared much larger in the sky than it does today. Because it was closer to Earth, its size seemed enormous, dominating the night sky. People living at that time would have seen a moon that looked bigger and brighter than what we are used to now. Over time, as the moon slowly moved farther away due to the transfer of energy from Earth, it began to appear smaller. This gradual change took millions of years, but it transformed the way the moon looks to us. Even though the moon seems constant and unchanging tonight, its appearance has slowly evolved over the history of the planet. The large, close moon of the past would have created stronger tides, affecting oceans and coastlines more dramatically. This fact reminds us that gravity is not just a present force, but also a powerful influence shaping Earth and the moon over extremely long periods, quietly changing what we see in the sky. Gravity has another fascinating effect on the moon. It causes the moon to always show the same face to Earth. This means that no matter where you are on our planet, you always see the familiar near side of the moon, with its dark and light patches. You never see the far side from Earth without the help of satellites or spacecraft. The reason this happens is because of the interaction between the moon's rotation and the pull of Earth's gravity over millions of years. The gravitational pull has slowed down the moon's rotation to match its orbit around Earth. This synchronization is precise, so the moon rotates exactly once for every orbit. The result is a consistent face toward our planet, creating a sense of stability and familiarity. This effect is another example of gravity shaping motion and rotation over vast timescales, quietly controlling how celestial bodies behave. This phenomenon, where the moon always shows the same side to Earth, is called tidal locking. Tidal locking happens when the gravitational forces between two objects create a stable pattern over time. In this case, Earth's gravity influenced the moon's rotation until it synchronized with its orbit. Tidal locking is not unique to the moon. It happens with many moons in the solar system. For example, some of Jupiter's and Saturn's moons are also tidally locked with their planets. This effect takes millions or even billions of years to occur, showing how slow and patient gravity's influence can be. Once tidal locking happens, it becomes permanent unless a huge force intervenes. The moon's consistent orientation is a direct result of this process. Understanding tidal locking helps scientists predict how other celestial bodies behave and explains why we have always seen the same face of the moon throughout human history. It is a quiet, invisible effect of gravity's long-term work. Because of tidal locking, one side of the moon has remained hidden from human eyes for most of history. Before the age of spacecraft and lunar satellites, no human had ever seen the far side. People could only observe the near side, the part of the moon illuminated by sunlight and visible from Earth. This hidden side remained a mystery, and even today, it looks very different from the side we see. The far side has more craters and fewer dark plains compared with the familiar near side. This separation between visible and hidden faces exists because gravity caused tidal locking, synchronizing the moon's rotation with its orbit. The hidden side reminds us that gravity is not just a force pulling objects together, but also a force shaping orientation, motion, and the way we perceive celestial bodies. Even the moon, one of the closest objects to Earth, has secrets controlled by the quiet but powerful hand of gravity. Every planet in the solar system has its own gravitational strength, and it is different from Earth's. Gravity depends on the planet's mass and size. Larger planets or those with more mass generally have stronger gravity, while smaller or less dense planets have weaker gravity. This means that objects and people would weigh different amounts depending on the planet they are on. For example, an astronaut who weighs 70 kilograms on Earth would weigh much less on a smaller planet and much more on a larger one. Gravity controls not only weight, but also how objects move near the planet. It affects jumping, walking, and even how liquids behave. Understanding each planet's gravity is important for space travel and planning missions. Scientists carefully calculate gravitational forces to predict spacecraft trajectories and landings. Even though planets are all part of the same solar system, their unique gravity shapes their own environments, creating a fascinating variety of experiences across the universe. On Mars, gravity is much weaker than on Earth, at only about 38% of our planet's pull. This means that if you weigh 100 kilograms on Earth, you would feel like you weigh just 38 kilograms on Mars. The lower gravity is due to Mars being smaller and less massive than Earth. As a result, the pull toward its center is weaker. This change in gravity would affect everything a human does. Walking, running, or lifting objects would feel very different. Even liquids and gases would behave differently, floating more easily and moving more slowly compared with Earth. Scientists take this into account when designing rovers and habitats for Mars missions. Lower gravity also affects the human body over time, including muscles and bones, which adapt to the weaker pull. Understanding Mars' gravity helps astronauts prepare for life on another planet, showing how gravity shapes not only movement, but also biology and engineering in space. Because gravity on Mars is weaker, people could jump much higher than on Earth. The reduced pull means it would take less effort to lift off the ground. For example, a person who can jump half a meter on Earth could jump almost 3 times as high on Mars. This would make walking and running feel lighter and easier, almost like bouncing with each step. Sports, construction, and even simple daily movements would be very different compared with Earth. However, the low gravity also means that balance and coordination would need to adjust. Falling or landing would feel unusual, and over time, muscles would adapt to the lighter environment. Understanding this effect is important for astronauts who plan to spend long periods on Mars, because their bodies would need to gradually adjust to the weaker pull. Gravity, even when weaker, continues to shape movement, physical effort, and the way objects interact on any planet, creating a completely new experience for humans away from Earth. Jupiter, on the other hand, has an enormous gravitational pull, more than twice that of Earth. Its massive size and mass make its gravity incredibly strong. Standing on Jupiter, if it were possible, a person would feel much heavier, and even lifting small objects would become very difficult. The strong gravity affects everything near the planet, including its moons and the dense atmosphere surrounding it. Jupiter's gravity is so powerful that it helps protect the inner solar system by pulling in or capturing comets and asteroids that might otherwise enter Earth's neighborhood. The strong pull also shapes the paths of its many moons, keeping them in stable orbits over billions of years. Scientists studying Jupiter must account for this intense gravity when sending spacecraft close to the planet. Gravity on Jupiter shows how mass and size can create extreme conditions, completely different from what we experience on Earth, and highlights the incredible variety of forces acting across the solar system. Standing on Jupiter would be an entirely different experience compared with Earth, if only there were solid ground to stand on. Because its gravity is more than twice as strong as Earth's, your body would feel extremely heavy. Every movement, from lifting your arms to walking, would require far more effort. Even simple actions that feel effortless on Earth would become challenging under Jupiter's intense pull. Unfortunately, Jupiter does not have a solid surface like Earth. It is mostly composed of thick gases, clouds, and liquid layers deep below. If humans tried to land, they would sink into its dense atmosphere long before reaching any solid material. Scientists and engineers must carefully consider Jupiter's gravity when sending spacecraft near the planet, because it strongly affects speed, trajectory, and fuel requirements. Jupiter's extreme gravity is a striking reminder of how mass shapes forces in the universe, creating environments that can feel unimaginable compared with the gentle gravity we experience every day on Earth. Gravity, in this case, dominates movement and survival entirely. The Sun has the strongest gravity in the entire solar system, far exceeding the pull of any planet. Its mass is enormous, containing more than 99% of all the matter in the solar system. This extreme gravity is what allows the Sun to hold all the planets in stable orbits, keeping the solar system organized. Without the Sun's gravitational pull, planets would travel in straight lines into space, no longer following circular or elliptical paths. Even distant objects, such as comets, asteroids, and dwarf planets, feel the Sun's gravity, guiding their motion across billions of kilometers. The strength of its pull decreases with distance, but it is still dominant compared with any other force in the solar system. Understanding the Sun's gravity is essential for calculating spacecraft trajectories, predicting planetary motion, and studying the behavior of objects at the edge of the solar system. Its massive gravitational influence is a central reason why life on Earth exists in a stable and predictable environment. The Sun's gravity is so powerful that it holds all the planets firmly in orbit, from Mercury closest to the Sun to Neptune at the edge of the solar system. Every planet is pulled toward the Sun, yet at the same time, each planet is moving forward through space. The combination of this forward motion and the Sun's pull creates stable orbital paths, preventing planets from falling into the Sun or escaping into space. This delicate balance has lasted for billions of years, ensuring the predictable motion of planets and the stability of the solar system. Even tiny variations in gravity could have major effects on planetary motion, which is why understanding the sun's influence is so important for astronomers. Without the sun's immense gravity, Earth would not have seasons, predictable days, or stable conditions for life. Gravity acts quietly but powerfully, connecting the sun with every planet and object in the solar system, orchestrating motion on a massive scale. Even distant comets and objects in the far reaches of the solar system are controlled by the sun's gravitational pull. These icy bodies travel in elongated orbits that stretch far beyond the planets, sometimes taking hundreds or thousands of years to complete a single journey around the sun. Despite being so far away, they are still influenced by the sun's gravity, which guides their paths and prevents them from moving in straight lines into empty space. When comets pass closer to the sun, the gravitational pull speeds them up, bending their motion and sometimes creating spectacular visible tails as heat causes ice to vaporize. The sun's gravity not only organizes the planets, but also governs the motion of countless small objects in the solar system, creating order even at enormous distances. This shows that gravity works over vast ranges, shaping motion and movement in ways that are invisible but consistently powerful, controlling everything from massive planets to tiny, icy visitors from the edge of space. Without the sun's gravity, the entire solar system as we know it would not exist. Planets, moons, asteroids, and comets rely on the sun's immense pull to stay in their orbits. Without this invisible anchor, these objects would travel in straight lines into space, no longer following the circular or elliptical paths we observe. The planets would no longer revolve around the sun, and the carefully balanced order of the solar system would collapse. Earth, along with all life on it, would be thrown into an unpredictable trajectory, making survival impossible. Gravity from the sun keeps everything connected, from the largest planets to the smallest asteroids, creating stability across billions of kilometers. Even objects at the very edge of the solar system, like distant comets and dwarf planets, remain under the sun's influence. This illustrates how crucial gravity is in maintaining order in space, acting as a quiet, invisible force that holds the entire solar system together over billions of years, shaping the cosmos in ways we often take for granted. Gravity acts like an invisible anchor holding everything together, not just in our solar system, but throughout the universe. It keeps planets circling stars, moons circling planets, and even galaxies connected over enormous distances. Without gravity, stars would not form from clouds of gas, planets would not gather from dust and rocks, and entire galaxies could not exist. Gravity pulls matter together, shaping the structure of the universe and controlling motion on every scale. From objects as small as pebbles to vast clusters of stars, gravity creates connections that are invisible but essential. Even black holes, some of the densest objects in space, bend gravity so strongly that nothing can escape them. In everyday life, gravity anchors oceans, holds our atmosphere in place, and keeps us firmly on the ground. Although we cannot see it, gravity is constantly at work, linking everything with mass into a stable and predictable system, quietly maintaining order across time and space. In the early 1900s, a new understanding of gravity emerged, thanks to Albert Einstein. Scientists had long thought of gravity as a force that pulled objects together, following the rules described by Newton. However, Einstein introduced a revolutionary idea that changed everything. He suggested that gravity is not simply a force acting at a distance, but is instead related to the structure of space itself. This new perspective explained phenomena that Newton's laws could not fully account for, such as the precise motion of Mercury around the sun. Einstein's work opened the door to modern physics, connecting gravity with space and time in a deeper way. His ideas allow us to understand not just planets and stars, but also the behavior of light near massive objects, the formation of black holes, and the expansion of the universe. Gravity, under Einstein's view, becomes a feature of space itself, not just a pull between objects. Instead of thinking of gravity as a force pulling objects together, Einstein described it as the bending or curving of space. Imagine placing a heavy ball on a stretched fabric. The fabric sinks under the weight, creating a curve. If you roll a smaller ball across the fabric, it moves along the curves, following a path that seems like it is being pulled. Similarly, massive objects like planets and stars bend the fabric of space around them. Objects moving near them follow these curves, which we observe as the effect of gravity. This explains why planets orbit the sun, why light bends near massive stars, and why black holes trap everything nearby. Gravity is no longer just an invisible tug. It is the shape of space itself guiding motion. Einstein's idea gives us a deeper understanding of how the universe works, showing that every object with mass influences the very structure of the cosmos, creating paths and patterns we can observe. Massive objects like stars and planets have an incredible effect on the space around them. According to Einstein's theory, these objects warp or bend the fabric of space, creating curves and dips. The bigger the mass, the stronger the bend in space. This curvature is what we perceive as gravity. It is not simply a pull, but the way space itself is shaped by matter. Even though we cannot see space bending, we can observe its effects everywhere. Planets orbit stars, moons orbit planets, and satellites stay in paths that follow these curves. Light itself is affected, bending slightly when it passes near massive objects. This bending explains phenomena like gravitational lensing, where distant galaxies appear stretched or magnified. Gravity, in this sense, is a property of space, not just an invisible force. Understanding this helps scientists predict the motion of objects across the universe, from nearby planets to distant stars, showing the quiet, continuous influence of massive bodies on the cosmos. Objects move along the curves created by massive bodies in space, and this is why they appear to be pulled by gravity. For example, Earth moves around the sun because the sun's mass bends the space surrounding it. The Earth is following the curves in space, and this motion creates the orbit we observe. It is similar for the moon around Earth, or satellites moving around planets. These objects are not being pulled in the old Newtonian sense, but are following paths shaped by curved space. This idea also explains why light from distant stars bends when it passes near massive galaxies. The apparent pull is simply the result of moving along these natural curves. Everything with mass affects space, and everything moving near it follows the paths created by those bends. In this way, the universe is a web of curved paths, with motion directed by the structure of space itself, rather than by invisible forces acting across distance. A common way to visualize this concept is by imagining a heavy ball placed on a stretched rubber sheet. The weight of the ball sinks the sheet, creating a dip around it. This dip represents the way massive objects bend space. If you place a smaller ball on the sheet nearby, it will naturally move toward the heavier ball along the curves formed by the dip. It does not need to be pulled. Its motion follows the contours created by the heavier object. This simple model helps explain why planets orbit stars and why moons follow paths around planets. The dip in the sheet is like the curvature of space, and the smaller object's motion represents how gravity guides their paths. By thinking of gravity this way, we can better understand the invisible structure of space and the predictable motion of celestial bodies, showing the elegant logic behind cosmic movement. When smaller balls roll near a heavier ball on a stretched rubber sheet, they naturally spiral toward the heavier object. Their paths curve along the depressions created by the mass, moving as if guided by invisible lines. This spiraling motion is similar to how planets move around the sun, or how moons circle planets. They follow the curves in space rather than being pulled directly. The speed and angle of motion determine the shape of the orbit. Faster motion can create wide, elliptical paths, while slower motion can create tighter spirals. This simple analogy demonstrates how gravity, as the bending of space, controls motion without any force acting at a distance in the traditional sense. It shows that the universe operates with predictable patterns, where mass shapes the paths of objects, and objects follow those paths naturally. Even complex orbits can be understood by imagining how objects move along curved space, revealing the quiet power of gravity in action. This bending of space explains how gravity really works in a way that is different from the old idea of a simple pull. Instead of imagining an invisible force pulling objects together, we now understand that massive objects shape the space around them, and other objects move along those shapes naturally. Planets, moons, and satellites all follow paths determined by the curves created in space by heavier bodies. Even Earth's orbit around the Sun is an example of this curved space guiding motion. This perspective helps scientists predict how objects will move over time, and it explains why orbits are stable and predictable. The bending of space is subtle, yet it affects everything from small rocks in space to entire planets. It is a continuous, invisible influence shaping motion across the universe. By understanding gravity this way, we can see the universe not as a collection of objects pulling on each other, but as a dynamic, connected fabric where mass guides movement through curved space. Even light, which has no mass, follows these curves when passing near massive objects. This is surprising because light travels incredibly fast and is not affected by forces like gravity in the traditional sense. Yet, because massive objects bend space itself, light moves along the curved paths created by that bending. When light from distant stars or galaxies passes near planets, stars, or black holes, its direction changes slightly, creating observable effects. This demonstrates that gravity is not just a force acting on objects with mass, but a property of space guiding motion. Observing how light bends helps astronomers study the structure of the universe, including the presence of invisible matter. The fact that even massless light follows these curves is one of the most striking proofs of Einstein's theory. Gravity, in this sense, is not just a pull. It is the shape of space guiding everything that moves within it, even light itself. This bending of light near massive objects is called gravitational lensing, a remarkable phenomenon predicted by Einstein and confirmed by observation. Gravitational lensing occurs when the curved space around a massive object, like a galaxy or black hole, changes the path of light coming from a more distant object. The effect can magnify, bend, or even create multiple images of the background object. Scientists use gravitational lensing to study galaxies that would otherwise be too far or faint to see. It also allows them to map invisible matter, like dark matter, by observing how light bends around it. Gravitational lensing shows that space is flexible and that mass can shape it in ways that affect motion and observation. Even though we cannot see space bending with our eyes, we can detect its effects through light, revealing the hidden influence of gravity across billions of kilometers in the universe. Distant galaxies can appear stretched, warped, or even duplicated because of this bending of space. As light travels from these galaxies toward Earth, it passes near massive objects like clusters of galaxies. The curved space around these objects alters the path of light, making galaxies appear in different positions or shapes than they actually are. Sometimes a single galaxy appears as multiple images, creating a cosmic mirage. This effect is not just beautiful, it provides astronomers with valuable information about the distribution of mass, including invisible dark matter. By studying these distortions, scientists can understand the structure and growth of the universe. Gravitational lensing demonstrates that gravity is not only a force shaping motion, but also a tool for observing distant parts of the cosmos. The bending of light reveals the hidden connections between mass, space, and energy, showing how gravity influences the universe on scales far beyond what we can directly see. Some objects in space have gravity far stronger than anything we experience in our solar system. These objects are not just massive, they are extremely dense, meaning a lot of mass is packed into a very small space. Their gravity is so strong that it warps space and time around them in extreme ways. For example, black holes and neutron stars create gravitational fields that can pull in nearby objects, including light itself. Even spacecraft would struggle to escape such strong gravity if they got too close. These intense gravitational forces shape the behavior of nearby matter, bending its motion, controlling orbits, and even creating spectacular cosmic phenomena like accretion disks and jets of energy. Gravity in these extreme cases is far beyond what we encounter on planets like Earth or even gas giants like Jupiter. Studying these objects helps scientists understand the limits of physics, the behavior of matter under extreme conditions, and the true power of gravity in the universe. Neutron stars are one of the most fascinating examples of objects with extraordinary gravity. They are the dense remnants left behind after a massive star explodes in a supernova. During the explosion, the outer layers of the star are blown away, but the core collapses under gravity to an incredibly small size. Despite being only about 20 kilometers across, neutron stars can contain more mass than the Sun. This extreme density creates a gravitational pull that is immense, far stronger than anything in our solar system. Neutron stars rotate rapidly, sometimes hundreds of times per second, and they can emit powerful beams of radiation detectable across vast distances. Their gravity affects nearby stars, gas, and even light, shaping their motion and creating observable phenomena. Neutron stars demonstrate how gravity can dominate on a scale far beyond planets or ordinary stars, showing the universe's power and the extremes that exist in space. A teaspoon of neutron star material would weigh billions of tons on Earth, illustrating just how dense these objects are. Imagine holding a tiny amount of substance that contains more mass than entire mountains combined. The atoms in a neutron star are compressed tightly together, leaving almost no empty space. This is possible because the star's gravity has overcome the normal forces that keep atoms separated. If you could somehow bring even a small fragment of a neutron star to Earth, it would instantly crush everything around it under its immense weight. Scientists study neutron stars to understand how matter behaves under these extreme conditions, which cannot be replicated in laboratories on Earth. This extraordinary density shows how gravity can compress matter to limits beyond ordinary experience. Neutron stars are natural laboratories, revealing the extreme effects of gravity and the incredible range of mass and density that exists in the universe. The gravity of neutron stars is so intense that it compresses atoms together in ways that are unimaginable on Earth. Normal atomic structures cannot resist the force, so electrons and protons are forced into neutrons, creating a material that is almost entirely neutrons. This compression results in extraordinary density, making the neutron star extremely heavy for its size. The gravitational field near its surface is so strong that time itself slows down slightly, a phenomenon predicted by Einstein's theory of relativity. Even light that passes too close can be bent dramatically or trapped entirely. This extreme gravity shapes the neutron star's surroundings, influencing the movement of gas, dust, and even nearby stars. Studying these stars helps scientists test the limits of physics and understand how matter behaves under extreme forces. Neutron stars demonstrate that gravity is not just a gentle pull, but can become a dominating, compressive power that transforms matter and space itself in extraordinary ways. Even stranger objects exist in the universe called black holes, and they are among the most mysterious and powerful objects known to science. Black holes are invisible in the traditional sense because they do not emit light, yet their presence can be detected by observing the behavior of nearby stars, gas, and dust. They warp space and time so intensely that anything passing too close is affected in extreme ways. Some black holes are small, formed from individual stars, while others are supermassive, containing millions or billions of times the mass of the Sun. Their gravity dominates everything in their vicinity, controlling the motion of matter over vast distances. Black holes are natural laboratories for understanding the limits of physics, extreme gravity, and the bending of space. Observing them allows scientists to study phenomena that cannot occur anywhere else in the universe, making black holes not just strange, but also essential to understanding how gravity shapes the cosmos on the most extreme scales imaginable. Black holes form when massive stars collapse under their own gravity at the end of their life cycles. When a star much larger than the Sun exhausts its nuclear fuel, it can no longer support itself against the pull of its own gravity. The core collapses inward, crushing matter into an incredibly small and dense point, while the outer layers may explode as a supernova. The result is a black hole, an object so dense that its gravity becomes extraordinarily strong. The more massive the original star, the stronger the resulting black hole's gravity. Black holes can grow even larger by pulling in surrounding matter, including gas, dust, and even nearby stars. This process makes them extremely influential in their regions of space, shaping the movement of everything around them. Understanding how black holes form shows the extreme power of gravity and how it can transform stars into objects that control their cosmic neighborhoods. The gravitational pull of a black hole is so strong that not even light can escape once it gets too close. This is why black holes appear completely dark, making them invisible against the background of space. Anything that comes within a certain distance is pulled in, no matter how fast it is moving. Gas, dust, and even entire stars can be captured by a black hole's gravity. As matter falls in, it often forms a rotating disk called an accretion disk, heating up and emitting powerful radiation before crossing the point of no return. The inability of light to escape is what makes black holes unique and mysterious. They are extreme examples of how gravity can dominate space, overpowering everything nearby. Observing the effects of a black hole on its surroundings allows scientists to study its presence, even if the black hole itself cannot be seen. This illustrates the ultimate power of gravity in the universe. The boundary around a black hole where escape becomes impossible is called the event horizon. Once anything crosses this invisible line, not even light or information can get out. The event horizon marks the point where gravity becomes so intense that all paths lead inward, toward the center of the black hole, which is called the singularity. From the outside, objects appear to slow down and stretch as they approach the event horizon, a result of the warping of space and time. Anything that crosses this boundary is lost to the black hole forever. Scientists study the event horizon indirectly by observing the effects of matter and light near it, including the bright radiation from infalling material. The concept of the event horizon helps us understand the limits of gravity and the extreme bending of space-time. It represents the ultimate boundary in the universe, where the pull of gravity becomes absolute, creating one of the most fascinating and mysterious phenomena in existence. If you approached a black hole, the gravity would become so extreme that it would stretch your body in a very unusual way. Because the gravitational pull near a black hole is much stronger at your feet than at your head, you would be pulled apart lengthwise. This stretching effect increases as you get closer to the black hole, becoming stronger and stronger. Scientists call this process spaghettification because the body would be stretched into a long, thin shape, almost like a piece of spaghetti. Even if you were incredibly strong, there would be no way to resist this force because the pull is far beyond anything we experience on Earth. Spaghettification shows how gravity can act in extreme and unusual ways under certain conditions. This effect is not just theoretical. It has been modeled by scientists using physics and relativity. Gravity, in this case, becomes an overwhelming, inescapable force, shaping matter in ways that are both fascinating and terrifying, revealing the extremes of our universe. This strange effect, spaghettification, occurs because gravity does not act equally at all points of an object. Near a black hole, the difference in gravitational pull between one side and the other is enormous. Your body, or any object, experiences tidal forces that stretch it along the direction of the pull. The closer you get to the singularity, the point at the center of the black hole, the more extreme the stretching becomes. The process is gradual but unstoppable. Nothing can resist it once inside the critical region near the event horizon. Studying spaghettification helps scientists understand how gravity behaves under the most extreme conditions, providing insights into space, time, and the limits of matter. It also demonstrates that gravity is not always gentle, like on Earth, but can become a dominant force that reshapes objects entirely. This extraordinary effect highlights the fascinating and sometimes dangerous power of gravity in the universe. Gravity also shapes entire galaxies across billions of light years, keeping stars, gas, and dust connected in coherent structures. Without gravity, galaxies would not form. Matter would simply float apart in space. The pull of gravity draws gas and dust together, allowing stars to form in clusters, while stars themselves are held in stable orbits around the galactic center. Gravity also influences the motion of galaxies within clusters, guiding their interactions and mergers over billions of years. Even the spiral shapes and patterns we see in galaxies are influenced by gravity, creating swirling arms and dense cores. Large amounts of invisible matter, known as dark matter, also contribute to the gravitational pull that holds galaxies together. Gravity acts over enormous distances, linking matter in ways that maintain order on cosmic scales. This demonstrates that gravity is not just a local force, but a universal architect shaping the structure and evolution of the universe itself. Our galaxy, the Milky Way, stays together because of gravity, which holds billions of stars, planets, gas clouds, and dark matter in orbit. The stars revolve around a dense center, likely containing a supermassive black hole, and the gravitational pull of this center, along with the combined gravity of all the stars and dark matter, keeps the galaxy intact. Without gravity, the stars would fly off into space, and the Milky Way would cease to exist as a coherent structure. Gravity also influences the motion of smaller satellite galaxies, keeping them bound to the Milky Way as they orbit around it. The spiral arms of our galaxy, full of young stars and gas, are shaped by gravitational forces acting over millions of years. Observing the Milky Way teaches us how gravity organizes matter on vast scales, maintaining stability and order. From the smallest planets to the largest galaxies, gravity is the invisible force holding the universe together, quietly shaping the cosmos over billions of years. Hundreds of billions of stars orbit the center of our galaxy, the Milky Way, each following paths determined by the combined gravity of all the matter around them. Every star, from the smallest red dwarf to the largest blue giant, is pulled by the mass of the galaxy, creating stable orbits that can last billions of years. These stars move at incredible speeds, yet they remain bound to the galaxy by gravity, circling the center like planets around a star. Even the Sun, our home star, travels at roughly 828,000 kilometers per hour, completing one orbit around the galactic center in about 225 million years. The motion of stars is not random. It is carefully orchestrated by gravity, which shapes the galaxy's spiral arms, dense cores, and vast halo. Gravity links all these stars into a coherent system, ensuring the galaxy's stability. Without this invisible pull, stars would scatter, and the Milky Way would lose its structure, demonstrating how gravity governs cosmic motion on massive scales. At the very center of the Milky Way lies a supermassive black hole, an object with millions of times the mass of the Sun. Its gravity is extremely strong, dominating the motion of stars, gas, and dust in the surrounding region. Stars that pass close to this black hole are influenced dramatically, sometimes moving at thousands of kilometers per second, tracing tight, rapid orbits around the invisible center. The black hole itself cannot be seen directly, but astronomers detect its presence by observing the motion of nearby stars and the radiation emitted as matter falls toward it. This supermassive black hole anchors the galaxy, contributing to the gravitational pull that holds the entire system together. Its influence extends across light years, shaping orbits and the distribution of matter near the core. Studying the black hole at the Milky Way's center gives scientists insight into how galaxies form, evolve, and maintain stability, illustrating the central role of gravity in the universe. The gravity of this central supermassive black hole influences the motion of nearby stars, dictating their orbits and speeds. Stars closer to the center move faster, responding to the immense pull, while those farther away follow more relaxed paths. This variation in motion helps astronomers map the mass and size of the black hole and understand the dynamics of the galaxy. Gas clouds near the center can be compressed or heated as they interact with the strong gravitational field, sometimes triggering new star formation. Even clusters of stars and smaller objects feel this pull, making the central region a complex and dynamic environment. The black hole's gravity also interacts with the combined mass of stars and dark matter, keeping the inner galaxy stable despite the chaotic activity near the center. Observing these effects allows scientists to see how gravity orchestrates motion on massive scales, linking individual stars with the overall structure of the Milky Way and shaping cosmic behavior across millions of light years. Galaxies themselves are not isolated. They orbit one another within clusters, bound together by the combined gravity of all the stars, gas, and dark matter they contain. These galaxy clusters can include hundreds or even thousands of galaxies, all moving in a complex cosmic dance. Gravity keeps the galaxies from flying apart, and over billions of years, their interactions can lead to collisions, mergers, or tidal distortions that reshape their structure. Even the motion of entire clusters is guided by gravity from neighboring clusters and superclusters, creating a vast network of cosmic structures across the universe. These gravitational interactions influence star formation, black hole activity, and the evolution of galaxies over time. Observing clusters of galaxies shows how gravity operates not just on a local scale, like stars orbiting a galaxy, but on unimaginably large scales, connecting vast regions of the universe. Gravity is the invisible thread weaving the cosmos together, linking galaxies, clusters, and superclusters in a grand, interconnected structure. Gravity also played a crucial role in forming the first stars after the Big Bang, shaping the early universe in remarkable ways. In the moments after the universe began, matter was spread out as a nearly uniform gas, mostly hydrogen and helium. Tiny variations in density created regions that were slightly heavier than others. Gravity acted on these denser regions, pulling surrounding gas toward them slowly but steadily. Over millions of years, this accumulation of matter caused clumps to grow larger and denser, creating the seeds for the first stars. Gravity guided the motion of gas, determining where stars would eventually ignite. Without gravity, matter would have remained scattered, and stars, galaxies, and planets might never have formed. This shows that gravity is not only a force we feel on Earth, but also a cosmic sculptor, shaping the universe from its earliest moments. It quietly orchestrates the formation of stars, galaxies, and the vast structures that define the cosmos today. Tiny clumps of gas in the early universe slowly collapsed under gravity, gathering more and more material as they became denser. These regions, slightly heavier than their surroundings, pulled in nearby gas through the gravitational attraction, creating larger and larger clouds. The collapse was gradual, taking millions of years, yet it was relentless. As the gas compressed, its temperature rose, eventually reaching levels hot enough to trigger nuclear reactions at the center. Gravity controlled how quickly matter gathered and where the densest regions formed, setting the stage for star formation. Even small variations in the gas distribution were amplified by gravity, creating a complex network of structures that would later become galaxies. This process illustrates how gravity works over vast scales and long periods, quietly shaping the universe without any visible force. From these tiny beginnings, the first stars appeared, showing that gravity is the engine behind cosmic evolution and structure formation. Over time, the densest clumps of gas ignited into the first stars, shining light into the universe for the very first time. The nuclear reactions in their cores created energy that allowed them to shine brightly, marking the transition from a dark, uniform universe to one filled with points of light. These early stars were massive and short-lived, burning quickly and often ending in spectacular supernova explosions. Gravity ensured that new clumps continued to form, sustaining star formation over billions of years. The first stars also began producing heavier elements through nuclear fusion, seeding the universe with the building blocks for planets and life. Observing distant galaxies allows scientists to see light from these early stars, revealing how gravity shaped the universe in its infancy. Gravity was the invisible hand that transformed simple gas clouds into glowing stars, beginning the long process of cosmic structure and complexity that continues even today. Gravity has been building cosmic structures for billions of years, connecting matter on scales from stars to entire galaxy clusters. From the collapse of gas clouds into stars to the formation of galaxies, clusters, and superclusters, gravity has continuously guided the universe's evolution. It shapes the paths of planets, holds galaxies together, and determines the motion of entire clusters of galaxies. Over cosmic time, Gravity pulls matter into increasingly complex structures, creating the web-like patterns we observe across billions of light years. Even invisible dark matter contributes to this process, adding mass that shapes the motion of galaxies and the formation of clusters. Gravity is slow and persistent, acting over immense distances and long timescales, yet it is remarkably effective. Every star, planet, and galaxy owes its existence and stability to gravity. Without it, the universe would remain a featureless expanse of gas. Gravity is the fundamental force building order from chaos, continuously sculpting the cosmos and connecting every object across space and time. Despite understanding its effects so well, gravity remains one of the most mysterious forces in the universe. We can measure it, observe it, and predict its behavior with incredible accuracy, yet its fundamental nature is still not fully understood. Unlike other forces like electromagnetism or the strong and weak nuclear forces, gravity acts on all objects with mass, no matter what they are made of. It shapes galaxies, guides planets, and even bends light, yet we still lack a complete explanation of how it works on the smallest scales. Scientists have tested gravity in countless experiments, from dropping objects on Earth to observing stars near black holes. But at the quantum level, gravity does not yet fit neatly with our other physical theories. This gap in understanding makes gravity both familiar and mysterious, a force we live with every day but still struggle to fully explain. Its subtle presence shapes the universe, yet hides secrets we are only beginning to explore. Scientists still do not know how gravity fits with quantum physics, which describes the behavior of the tiniest particles in the universe. Quantum physics works extremely well for atoms, electrons, and photons, explaining how they move and interact. But gravity, as described by Einstein, works on a completely different scale, governing stars, planets, and galaxies. The problem is that the equations for quantum physics and general relativity do not match when applied together. Near extremely small, dense objects like black holes or during the Big Bang, both quantum effects and gravity are important, yet current theories cannot fully explain what happens. This mismatch makes gravity one of the greatest puzzles in modern science. Scientists are searching for a framework that can combine gravity with quantum physics, a theory that would describe the behavior of the universe at all scales. Until then, gravity remains a force that is both familiar in daily life and mysterious in the deepest workings of nature. Finding a theory of quantum gravity is one of science's greatest challenges, because it requires reconciling two very different views of the universe. On one hand, general relativity describes gravity as the bending of space and time, working perfectly for stars, planets, and galaxies. On the other hand, quantum mechanics describes the probabilistic behavior of the smallest particles, where forces are exchanged through discrete units. A complete theory of quantum gravity would connect these perspectives, explaining how gravity operates at the tiniest scales and under extreme conditions. Such a theory could reveal the inner workings of black holes, the earliest moments of the universe, and even the nature of space and time itself. Scientists are exploring ideas like string theory, loop quantum gravity, and other approaches to unify these concepts. Solving this mystery would be a monumental breakthrough, giving humanity a deeper understanding of the force that has quietly shaped the cosmos since the beginning of time. Some theories suggest that gravity may involve tiny, hypothetical particles called gravitons, which carry the force of gravity at the quantum level. Unlike other forces, where particles like photons carry electromagnetic force, gravitons have not been observed directly, but their existence is predicted by certain quantum models. If gravitons exist, they would interact extremely weakly with matter, making them incredibly difficult to detect. yet they would be responsible for transmitting gravity between objects. This idea provides a possible link between gravity and quantum mechanics, offering a way to understand gravity as a particle-based force. Detecting gravitons would revolutionize physics, confirming the quantum nature of gravity and allowing scientists to study it in new ways. The search for these particles is ongoing, with experiments designed to observe subtle effects of gravitational waves or interactions at very small scales. Gravitons remain theoretical for now, but they represent one of the most intriguing possibilities in the quest to understand gravity's deepest secrets. But no one has directly detected gravitons yet, and this remains one of the biggest challenges in modern physics. Gravitons, if they exist, would be incredibly tiny and interact extremely weakly with matter, making them nearly impossible to observe with current technology. Scientists have proposed experiments to detect their effects indirectly, such as through subtle changes in gravitational waves or the behavior of particles under extreme conditions. Detecting a graviton would confirm that gravity operates at the quantum level, similar to other fundamental forces like electromagnetism. Until then, gravity is studied through its large-scale effects, from falling objects on Earth to the motion of stars and galaxies. Despite the mystery, the idea of gravitons helps physicists explore ways to unify quantum mechanics with general relativity. The search continues, showing that even a force we experience every day holds secrets that are still beyond our reach. Gravity, familiar yet enigmatic, quietly connects the everyday world to the deepest mysteries of the universe. Gravity is also responsible for ripples in space called gravitational waves, which are disturbances in the fabric of space-time caused by accelerating masses. These waves travel outward from their source at the speed of light, carrying information about cosmic events. Unlike light or sound, gravitational waves do not require matter to move through. They propagate through space itself, stretching and squeezing space as they pass. The strongest waves are created when massive objects, like black holes or neutron stars, orbit each other or collide. These ripples are incredibly faint by the time they reach Earth, but sensitive instruments can detect tiny distortions caused in space-time. Gravitational waves provide a new way to observe the universe, revealing events that might otherwise be invisible, such as black hole mergers or supernovae. This discovery confirmed predictions made by Einstein a century ago and opened a new window for astronomy, showing that gravity is not just a force but a messenger carrying secrets across the cosmos. These gravitational waves were first directly detected in 2015, confirming one of Einstein's most remarkable predictions from general relativity. The detection came from two merging black holes, each several times the mass of the Sun, orbiting closer and closer until they combined. The collision sent powerful ripples through space-time, which traveled billions of light-years before reaching Earth. Using highly sensitive instruments called interferometers, scientists measured distortions smaller than a fraction of a proton's width, demonstrating the incredible precision required to observe these waves. This detection not only proved that gravitational waves exist, but also provided a new method to study the universe. By observing these waves, researchers can learn about black holes, neutron stars, and other extreme events that are otherwise invisible with traditional telescopes. The 2015 discovery marked the beginning of gravitational wave astronomy, offering a completely new way to explore cosmic phenomena and understand the role of gravity in shaping the universe. Gravitational waves occur when massive objects, such as black holes or neutron stars, collide or interact in powerful ways. When these objects orbit each other or merge, they accelerate rapidly, creating ripples in space-time that propagate outward at the speed of light. The waves carry energy and information about the mass, speed, and distance of the objects involved, providing scientists with unique insights into events that cannot be seen with ordinary telescopes. Collisions of supermassive objects can release more energy in a few seconds than the sun emits over billions of years. Gravitational waves allow researchers to study the most extreme environments in the universe, including black hole mergers, neutron-star collisions, and potentially even events from the early universe. By detecting these waves, scientists gain a new perspective on gravity, seeing how it operates dynamically and actively shapes the cosmos. Gravitational waves reveal that gravity is not static but a living, moving force carrying the echoes of cosmic events across space and time. The collision of massive objects, like black holes or neutron stars, sends tiny vibrations through space itself, creating gravitational waves that ripple outward in all directions. These vibrations are extremely small by the time they reach distant regions, causing distortions in space-time far smaller than an atom, yet they carry valuable information about the event that created them. The waves are generated by the acceleration and merging of massive bodies, where gravity's pull is at its most extreme. As they move through space, these waves interact with nothing directly, passing through stars, planets, and dust clouds without being absorbed or blocked. Detecting them requires incredibly precise instruments capable of measuring minuscule changes in distance between objects. Even though the vibrations are subtle, they reveal details about the mass, speed, and energy of colliding objects billions of light-years away. These tiny vibrations are evidence that gravity is not static. It moves and transmits information across the universe, linking cosmic events in ways that are invisible to the naked eye. Gravitational waves created by these collisions can travel across the universe for billions of years, carrying information from their sources directly to us. As the waves propagate, they stretch and compress space-time slightly, passing through galaxies, stars, and planets without slowing down or losing energy in any noticeable way. This allows scientists to detect events that happened billions of years ago, giving us a window into the early universe. The waves act like messengers, traveling enormous distances and delivering clues about cosmic collisions, star formations, and black hole mergers. By studying these waves, astronomers can learn about regions of space that are otherwise invisible and understand how massive objects interact under extreme gravitational forces. The fact that these vibrations persist over such incredible distances shows that gravity is a universal, long-reaching force, linking events across time and space. Gravitational waves demonstrate that the universe is dynamic, and gravity is not only shaping objects locally, but also communicating the echoes of cosmic events across unimaginable distances. Gravity has been shaping the universe since the beginning of time, quietly guiding matter from the earliest moments after the Big Bang. In the first seconds, tiny fluctuations in the distribution of matter were amplified by gravity, pulling gas and dust into denser regions. Over millions and billions of years, this led to the formation of the first stars, galaxies, and clusters. Gravity acts constantly, without pause, organizing matter into structures that become more complex over time. Even as the universe expands, gravity continues to influence the motion of stars, planets, and galaxies, maintaining coherence in a constantly changing cosmos. From the tiniest particles to the largest galactic structures, gravity is the invisible architect behind the universe's organization. Observing cosmic structures today reveals the fingerprints of gravity, showing how it has guided the formation and evolution of everything we see. Gravity is the quiet, persistent force that connects the past and present, shaping the universe across billions of years. It quietly organizes matter into planets, stars, and galaxies, holding them together and guiding their motion through space. Without gravity, gas clouds could not collapse to form stars, and stars could not hold planets in orbit. Entire galaxies rely on gravity to maintain their structure, with billions of stars bound together and orbiting around dense cores or supermassive black holes. Even clusters of galaxies are held in place by the combined gravitational pull of all the matter within them, including invisible dark matter. Gravity ensures that cosmic systems remain coherent, allowing the universe to form complex patterns rather than being a chaotic collection of unconnected objects. It operates over vast distances, yet its effects are evident in the motion of planets, the shape of galaxies, and the behavior of entire clusters. From the smallest pebble to the largest supercluster, gravity silently links all matter, demonstrating its role as the master organizer of the cosmos, shaping everything with invisible, unending influence. Every step you take is guided by gravity, pulling your body steadily toward the ground and keeping your feet firmly planted. Without this invisible force, walking, running, or even standing would be impossible, because there would be nothing to hold you down. Gravity ensures that your weight presses against the earth, giving you the traction needed to move safely. It interacts with the muscles and bones in your body, allowing coordinated movement and balance. Even small movements like bending or lifting an object are affected by gravity, which defines how objects fall and how much effort is needed to move them. Walking might seem ordinary, but it is gravity in action, silently controlling every motion. Every step is part of a continuous interaction between your body and Earth's pull, illustrating that gravity is not just a distant cosmic force, but something you experience constantly. It connects you to the planet and makes motion, stability, and life itself possible. Every drop of rain falls because of gravity, pulling water from clouds down to the surface of the earth. Rain does not float or move randomly. It accelerates toward the ground under the constant pull of gravity. The shape of raindrops, their speed, and even how they splash are all influenced by this force. Gravity ensures that rivers and streams receive water, replenishing lakes and nourishing plants and animals. Without gravity, precipitation would not reach the land in a controlled way, and life on Earth would struggle to survive. Gravity also controls the water cycle by drawing melted snow, condensation, and runoff toward the oceans, where it eventually evaporates again, continuing the cycle. Even small droplets in fog or mist are subtly pulled toward the ground. Rain is a visible, tangible example of gravity's presence in everyday life, reminding us that this universal force shapes natural processes constantly and quietly, sustaining ecosystems across the planet. Even the air around you is held close to Earth by gravity, preventing it from escaping into space. Gravity keeps our atmosphere dense enough to breathe, providing the oxygen necessary for all life on land. Without this pull, the air molecules would spread out, and the protective layer around the planet would thin or vanish entirely. Gravity organizes the atmosphere into layers, influencing weather patterns, wind, and the distribution of clouds. It allows air pressure to exist, which affects everything from the boiling point of water to how airplanes fly. Even subtle phenomena like the rising of hot air or the falling of cool air are shaped by gravity's pull. Life on Earth depends on this invisible grip that keeps gases in place and maintains a stable environment. From the oxygen we inhale to the winds that shape climates, gravity quietly anchors the air, making life possible and the planet habitable. Without gravity, life as we know it could never exist, because everything on Earth relies on this force. Planets could not form, stars would not ignite, and water would not stay on surfaces. Without gravity, there would be no atmosphere, no rain, no oceans, and no stable ground to support plants and animals. The movements of creatures, from the smallest insect to humans, depend on a gravitational pull that defines motion and balance. Gravity also controls the tides, which influence ecosystems in coastal areas, and shapes the long-term climate by maintaining the planet's rotation and orbit. It ensures that planets stay in their orbits around the sun, providing the conditions necessary for life to survive. Gravity is not just a background force. It is an essential architect of existence, quietly enabling the structures, cycles, and processes that sustain life. Every living thing owes its stability and survival to the relentless, invisible pull of gravity that shapes the world around us. It keeps our oceans, atmosphere, and planet stable, ensuring that Earth remains a place where life can exist and thrive. The oceans are held in their basins by gravity, preventing water from floating off into space, and shaping tides that regulate ecosystems. Gravity also keeps the atmosphere layered and dense enough to provide breathable air, protecting life from harmful radiation and extreme temperature changes. Mountains, valleys, rivers, and plains all remain connected to the planet because gravity pulls everything toward Earth's center. Even molten rock inside the planet is shaped and contained by gravitational forces, influencing volcanic activity and the movement of tectonic plates. Gravity organizes matter at every level, from tiny water droplets to massive continents, maintaining the balance necessary for life. Without this invisible force, Earth would be a chaotic, uninhabitable place, lacking oceans, air, or a stable surface. Gravity's quiet, constant pull is what allows ecosystems, weather patterns, and the planet itself to remain steady, working silently to sustain the world we know. And while it governs the entire universe, gravity works silently, without fanfare or notice, yet its effects are everywhere. It controls the motion of planets around stars, the rotation of galaxies, and the interactions between clusters of galaxies across billions of light years. Gravity bends light, carries gravitational waves, and shapes the structure of space-time, all without stopping or weakening. Unlike forces we can see or feel directly, gravity is invisible, yet it is the most pervasive influence in the cosmos. Stars, planets, moons, and even black holes obey its pull, following paths dictated by this ever-present force. On Earth, it keeps you grounded, guides the flow of rivers, and shapes the rise and fall of tides. Across the universe, it organizes matter into complex structures, from galaxies to superclusters. Gravity's silent governance demonstrates its power and subtlety. It rules everything, yet we often notice it only when we stop and think about the world around us. Right now, as you relax and close your eyes, gravity continues its endless work, pulling every atom in your body toward the center of the Earth. Even as you lie still, gravity interacts with your muscles, bones, and organs, maintaining your balance and structure without conscious effort. The air you breathe, the water in your body, and every object around you are held securely by gravity's invisible hand. It allows your heart to pump blood efficiently, your lungs to inhale and exhale, and your body to remain connected to the planet. Beyond your room, gravity governs the motion of the moon, the tides in the oceans, and the orbit of planets around the sun. While you prepare to fall asleep, gravity operates on scales both enormous and tiny, silently shaping the motions of the universe. It is a constant presence, connecting you to Earth and the cosmos, performing its work without pause, quietly influencing every part of your life. Holding you gently to Earth, just as it holds the entire universe together, gravity is the invisible thread linking every object, planet, star, and galaxy. Its pull ensures that nothing floats away aimlessly, keeping systems in balance across vast distances. On the smallest scale, it gives weight and stability to every object you touch or see. On the largest scale, it orchestrates the motions of entire galaxies, clusters, and cosmic filaments. Gravity is both intimate and immense, guiding your footsteps while controlling the paths of celestial bodies millions of light years away. It quietly connects the very small with the very large, holding everything in a delicate but powerful balance. As you drift toward sleep, you can feel its presence in the weight of your body, the pull of your mattress, and the gentle firmness of the earth beneath you. Gravity is the ultimate silent caretaker, holding life and the universe together, performing its endless work without notice or fatigue.